Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 5, Bonus Material. In our lesson, we saw two important series that have convergence constraints. These are the geometric series for 1 over 1 minus x and the binomial series for 1 plus x to the alpha. Both of these are guaranteed to converge only when x is less than 1 in absolute value. Let's put these series to work in a problem in electrostatics. An electric dipole is a pair of equal and oppositely charged particles separated by a short distance. Now, this is a calculus class, not a physics class. Don't worry, you're not going to need to know this for the exam, but let's learn a little bit, have some fun with it. The electrostatic potential gives the potential energy of this dipole, this pair of charges, as a sum of point charge potentials. And what do I mean by that? Well, each charge has a potential energy associated to it. The pair of them together yields a potential energy that depends on your position. So let's say that you're at some location away from the dipole. You want to know what is the electrostatic potential. It's given by the following formula. V is equal to kq over d plus minus kq over d minus. What does that mean? Well, K is a constant, the Coulomb constant. Q is the amount of charge on each element of this dipole. And d plus and d minus are the distances, respectively, to the positive and the negative charge in the dipole. All right, that's the physics that we need. Let's do some math. Let's compute what this electrostatic potential V is in the case where you are standing at a distance d away from the positive charge and where d is much greater than r, the separation distance between the two charges in your dipole. Now, I'm going to assume that we are orthogonal to the dipole. That is, we're at distance d from the positive charge, but perpendicular to the orientation of the dipole. That means that the distance to the negative charge is, by Pythagoras' theorem, the square root of d squared plus r squared. So that in computing V, we get kq over d, the positive charge distance, minus kq over square root of d squared plus r squared. We could stop there, but let's simplify this as much as possible. If we factor out kq over d, then we get a 1 from the left term. From the right term, we get 1 over square root of quantity 1 plus r over d quantity squared. Well, at this point, we can try to expand that out using the binomial series. Recall, the binomial series is for something of the form 1 plus x to the alpha. In this case, alpha is negative 1/2. We're looking at 1 over the square root of something. And x is r over d quantity squared. Because the first two terms in the binomial series are 1 plus alpha x, we get the first two terms in the series applied here to be 1 minus 1/2 times r over d quantity squared. Simplifying, we see that the 1's cancel, and we're left with kq over d times 1/2 r over d quantity squared. Everything else is of higher order term in r squared over d squared. Let's remember that 1/2 r over d quantity squared. In fact, we'll set it over here, right next to the location, and consider what happens when we look a distance d away from that positive charge, but in a different direction. Instead of being orthogonal to the dipole, let's look parallel to it. Well, in this case, d plus remains the same. It is this distance, d. But now, d minus is a bit simpler looking. It is d plus r, the separation distance in the dipole. Now again, factoring out a kq over d, we get a term on the right-hand side that is of the form 1 over 1 plus r over d. We can expand this out using, if we like, the binomial series with alpha equal -1, or what that really is, the geometric series for 1 over 1 minus x, with x being equal to negative r over d. Writing out the first two terms of that series as well, we get 1 minus r over d. The ones cancel, just as before, and we see that up to the leading order term, our electrostatic potential is kq over d times r over d. Now, notice how different that is from before. By using different series, we see that the leading order terms in the electrostatic potential differ depending on how you are oriented with respect to the dipole. Inline potential is much stronger than orthogonal. This is just one example of how we can use different series in order to get a handle on various physical phenomena by expanding, ignoring the higher order terms, and retaining the leading behavior.